So here we are. We're going to cover the challenge lesson. This is lab number 3. I'm going to go through all 10 challenges. Okay? We're going to start a new measurement plan from scratch. So here we go. File, New. First thing we do is save our measurement plan and give it a name. And in this case, this is, again, lab 3. So we'll go lab 3, my initials, and in this case, V1. Next, I'm going to load the CAD model, CAD file, load, and we change the file type to step, and there's our 1, 2, 3 block step file. Let's open that up. First thing we do when we bring in a CAD model is heal the model, so CAD file, automatic healing. We simply click Build Geometry and OK, and the CAD healing is complete. Next, I'm going to set the colors for our model. CAD Settings. Simply click on Part Color. That locks that in. And then I go to Edges/Curves, and that also locks in those purple edges. Looks good. Next, we're going to create our base/start alignment. We're going to create a new base alignment using the standard method. We switch the CAD programming tool to extract features, get my primary datum A. Now I switch the CAD programming tool to define a circle on a cylinder, and we'll go ahead and get that circle in the center. Zoom in a little bit. There's a very nice circle. And finally, switch back to extract features and get our datum C on the right-hand side of the part. Our base alignment is complete, and this is verified because I see the trihedron here in the center of the CAD model where I expect it, and right next to it is the name of my program, indicating that this is the proper alignment for this program. I'm going to click OK, and we see the CAD origin, which are these fat arrows, now transfer to the base alignment origin. Next, I'll complete the clearance planes. Clearance planes from CAD model, we're going to use a 1-inch offset. Clearance planes are now complete. I can click the Fit button and verify that my clearance planes cover the entire part. Clicking OK to close that. Update clearance planes for defined features. I say yes, and the words incomplete remind me that I have to put probing points into those features. Next, we're going to go to our features list and open up plane 1. First thing I'll do is rename plane 1 to plane A, and we're going to add a polyline for our strategy. So we'll go to the strategy button. I'll choose the polyline tool. I'll double click to open up the polyline, and we'll switch our view to view from the +Z, and we'll do a fit so that we can clearly see what we're doing. I'll now click to program my polyline. Back and forth with a serpentine pattern. Also, once I've set the path, now I come over here and set my speed and feed. 0.240 is the speed of maximum accuracy, so we can go 0.480, which is double that, for a reasonable scanning speed. Our step width must be something less than 10 thousandths, and 5 thousandths seems like a reasonable number, as that will result in 2,590 points being taken on this surface. We want to always try and keep our number of points in a reasonable range, but certainly a large quantity. Zeiss has declared that if we do less than 200 points per feature when scanning, we will not be able to properly calculate form. If you take more than 5,000 points, then the computer will slow down a little bit. If you take more than 10,000 points, the computer may pause for a second or two after measuring the feature to calculate the answer. This looks good to me, so I'll click OK. The last thing is whenever we scan, we filter, and whenever we filter, the default setting is correct. I go to the evaluation settings, I turn on the filter, I click Apply, then OK, and this feature is complete. I'm now going to go to Circle 2, or Circle 1, excuse me, and rename it to Circle B. This is our datum B. I'll now go to the strategy. This is a threaded hole, so I'm going to put a helix in there. First, I delete the circle path that exists, and then I insert a new helix. I'm going to open up the helix. There is a 5/16 18 thread. the pitch of an 18 pitch thread is 0.055555 repeating. We're going to start our measurement one thread pitch below the nominal location, so minus 0.055555. Then we will finish at plus one thread pitch, 0.055555. Again, the number of fives you put in there must be the same in both the top and the bottom. Number of rotations will be 2. And this gives us a nice helical path that starts one rotation below the nominal circle and finishes one rotation above the nominal circle and follows the helix of the thread to give us a more accurate locational measurement. Next, we need to set our number of points. When measuring a circular object, our number of points should be 500 points per revolution. We are doing 2 revolutions, so we need to do 1,000 points minimum. This is a minimum number, not a maximum number. Once I've set the number of points, I hit the Calculate button and choose Form so that the machine will calculate an appropriate speed. The machine might also choose to add more points if it feels that's necessary for an accurate measurement. Click OK, and once again, when we scan, we filter, and when we filter, the default setting is always correct. Finally, we'll do plane number 3, or plane 2, which is going to be plane C. And again, we're going to put a polyline in here. Strategy, insert polyline. We'll open up this polyline, and we'll take that measurement. 1, 2, 3, 4, and 5 to make a nice box type pattern. Again, we'll set our speed to 0.480. And in this case, again, we'll accept 5 thousandths as a reasonable step width. We'll click OK. I want to point out that there is a value for edge deviation. The edge deviation is how close the machine will follow the programmed path. It's how much it will round the corners. We tend to want to keep that number fairly small. 5 thousandths is a very reasonable number. Once again, when we scan, we filter, and when we filter, the default setting is always correct. Okay, we've now set up our 3 base alignment datum elements, and we can run our program to run the manual alignment. Plan, CNC start, starting on the right, feature list, clearance planes, normal, reduced speed for safety, use custom printout, clear existing results, and of course, current alignment is not the correct choice. We instead want manual alignment, and we're going to measure all characteristics. We'll click OK, and now I will execute the manual alignment. First, I need to take a minimum number of points on the top surface. In this case, I will take 4. Click OK to move on to the next feature. Now I need to measure some points in that circle. There we go. And again, OK to move to the next feature. Finally, I need to take some points on the datum C surface. 1, 2, 3, 4. And OK. Machine being switched to CNC mode, so I'll drive my probe up above my part to a safe position and click OK. Program has now been executed. Next, we begin the 10 challenges. The first challenge, the location, X value, Y value, and size, diameter, of the hole at the back left corner on top. The nominals are given on the worksheet. So we switch our tool here. Define a circle on a cylinder. Go ahead and create that circle. The first thing is we're going to open the circle up, go to the strategy, go and open the circle path, and hit the Calculate button, choose Form, and allow the machine to choose an appropriate speed and number of points for this measurement. I then click OK, OK. When we scan, we filter. When we filter, the default setting is always correct. We apply the filter. And now I press F9 to execute that feature now and test run it. You see that the machine has test ran the feature. I'll now generate the 3 characteristics required by the lesson. We want the x location. I now set the tolerance. I'm going to use plus or minus 10 thousandths. I hit enter, it goes to the next field, minus 0.01. If I hit enter again, it'll go to the identifier where I can call this dimension 1 or some other identifier. For the purpose of this lesson, I'm not going to rename features. Now we have before we do y, we switch our tolerance class to last input, and then we'll output y and diameter as well. The second challenge, the perpendicularity of a cylinder front and center to the primary datum plane. So I'm going to start by going and getting the perpendicularity characteristic. We'll see it has inserted itself in the list here. I open up the perpendicularity characteristic, I switch my CAD programming tool to extract features, and I extract the cylinder from the front center. We see that that cylinder automatically plugs itself in over here. Next, I need the primary datum. I switch my CAD programming tool to select already extracted features, and I select the datum on top. So now we've filled out this perpendicularity characteristic, and we'll put in our tolerance, which in this case is 1/1000th of an inch. Always hit enter when you type something in, and now this characteristic is also complete. I'm now going to go over to my features of the cylinder itself, and when I go to the strategy, I simply need to open up the circle path. Once again, I hit the calculate button to optimize. Now the machine has looked at the existing tolerance, the GD&T that I created, and determined an appropriate speed for the evaluation of that tolerance. I'll click OK. Once again, when we scan, we filter. And when we filter, the default setting is always correct. Once again, I will use an F9 to test this feature. There it goes. And if I wanted to double check the characteristic, I have some results now. Next, the 2 Cartesian distances, hole-to-hole distances, using the 3 holes along the left side. I'm once again going to switch my CAD programming tool to define a circle on a cylinder and get the next 2 holes that I need along the left side. I have already optimized circle 1, and so I just want to take its settings and apply them to circles 2 and 3. So I come up here to the format painter, the little paintbrush, the same format painter that is in Microsoft Word or Excel. I click on that, and I say that I want to transfer the evaluation settings and the measurement strategy from circle 1 and apply that to circle 3, and 2 and 3. I click OK, and now if we double check inside of circle 2, we can see that the filter has been set as well as the strategy has been optimized. Now I'm going to execute the distances called out by the lesson. Size, distance, Cartesian distance. I'm going to open that up. Once again, select already extracted features, and I'm going to get this circle and this circle. I need a primary datum across which the distance happens. That'll be this one. I need a secondary datum that gives me the orientation of my measurement. That'll be this datum over here. You can see now that we have 1.1 plus or minus 10, and everything looks very good. I'm going to take my first Cartesian distance, Control-C copy, Control-V paste, and now I'm going to open up the pasted copy. I have distance from circle 1 to circle 2, and now I need the distance from 2 to 3. I simply highlight where it says 1, type 3, and enter, and now I have the distance between 2 and 3. So quickly, I've created both of the characteristics I'm looking for, and once again, I can come back here, Shift, F9, and execute and test both features. It is important to test everything as you go along so that when you finish your program, you'll know that every element of the program already works and you can run your entire program safely. Next, we're going to do a simple distance, x and y, between the hole in the front left corner and a hole in the back right corner. So once again, I can start with the simple distance. I'll open that up. I have the Select Already Extracted Features tool is already active, and so I can simply get this one here. Next, I switch to Define a Circle on a Cylinder, get the opposite corner, and of course I want to know the x and y distances between these elements. Once again, I can get the settings for circle 4 by going to one of my previously set circles, go to the Format Painter. You'll see the checkboxes I'm using are still highlighted from before, so I simply highlight circle 4, click OK, and now the settings have also been applied there. I press F9, and now we've test ran circle 4 as well. Next, we'll be doing an angle between features, tolerancing two lines constructed from the three holes along the left side and the three holes that run diagonally across the block. By the way, the circle names are given in the lesson, but if you rename your circles here to circle B, then your numbers in the lesson will not match. Okay, so don't get caught up on that detail. Next, I'm going to go ahead and create the two lines. Feature, and we'll see there's two kinds of lines. There's a 2D line and a 3D line. The 2D line has a shadow, like it was drawn or exists physically. The 3D line shows three circles connected together with an axis. Whenever we want to physically measure a line on the part, that's a 2D line. Whenever we want to recall elements together to construct a line, that is a 3D line. No, they're not 2D and 3D. These are just the labels given to them. Okay, we open up the 3D line, nominal definition options, and recall. We then highlight those elements that we wish to recall into a line. In this case, it's going to be circle 1. Holding the control key down on the keyboard, circle 2, and circle 3. Click OK, and we can now see the line that I've constructed between the three of them. I'll create another line. Features, 3D line. Again, we open this line up. Again, nominal definition options recall. And this time I need circles 3, B, and 4. It is important to select them in a linear order. Click OK, and I have my second line. Now I need to get the angle between these two lines. That's a special type of characteristic, form and location, angle between features. I'm going to open up the angle between features and get my 3D line 1. By the way, these buttons at the top are filters. If I only want to see the 3D lines, I click that, and now that's all I see. This can be helpful when your programs get very long. And there's my two lines. Now the target value that I'm looking for is 28.6 degrees. And I can clearly see that this is some kind of complementary angle to 28.6 degrees. So what we have are 4 buttons here that show us the 4 complementary angles that are possible when two lines intersect. For most people, the easiest thing to do is just click the 4 buttons until you find an actual that is very close to what you're looking to measure. Now, a lot of times people will say to me, gee, I see this arrangement and it looks like it should be this picture. But be careful. These are not showing the acute angle between these. These lines in these pictures have an arrowhead. The arrowhead indicates the vector. When we constructed these lines, this line went 1, 2, 3, so its vector goes this way. When we constructed this line, it goes 1, 2, 3, so its line goes this way. So the two positive vectors are here, okay? What we're looking for is this is the angle between two positive vectors. This is the angle between a positive vector and a negative vector. This is the complementary angle between two positive vectors, and this is the complementary angle between a positive vector and a negative vector. So the vector direction of the line affects which of the choices you'll use for this calculation. Once I've selected the correct choice out of the 4, I can set my nominals, and in this case I'm going to go with, thank you, 28.6, and we'll click OK. The next challenge, the overall length and width of the block using a special type of element called a symmetry point. A symmetry point is not a symmetry construction that you may have seen on other coordinate measuring machines. It is a special type of element used to check distance and center location. To program it, I choose the Define Points tool from the CAD programming toolbar, and I simply click on one side of the part and then the other side of the part. We'll see that we now have symmetry point 1 and that it has a distance. I can check the box next to distance, and there's my value. Click OK, and we'll see that a dialog pops up. New generation of several clearance data in feature, question, may be necessary for detour generation as outside feature uses different styli. If yes, a clearance plane is generated for every probe point or segment. If no, you, the programmer, have to make sure that navigation is collision-free by setting intermediate points manually. Clearance planes that are already generated are retained if you answer no. So basically what this says is because we've just measured the outside of the part and the probe cannot go through the part to get from one probing to the other, that the machine is going to generate an extra clearance move to go up, over, and around the part to get to the probing on the opposite side. If you already programmed extra moves, say no so that the moves you programmed stay there. But if you didn't program extra moves, say yes so the machine can do it for you. Most of the time you will say yes. We say yes, and just to show you what that looks like, I'm going back into the strategy, and here we can see that it goes clearance data, probing point, clearance data to go back to the clearance plane, and then another probing point. And we'll create our second symmetry point. Again, this time the X width of the block. 1, 2, distance, OK, yes, done. And by the way, we will now test run both of those. F9, and looks good. And yes, those did generate these specific characteristics with these very long names on them. Those are names that are worthy of shortening a little bit. Next, we have the true position with MMC of the 5 holes on the right side of the block. That's these 5 holes over here. Before I program those 5 holes, I have to change my active stylus. So I come to the pull-down menu, and I'm going to activate the -X or number 5 stylus. Now I switch my CAD programming tool, define a circle on a cylinder, and I'm going to program that circle right there. Oops, it inserted in the middle of my list. Let me go ahead and move it down. I'm going to first optimize the speed and filter. So again, I find a similar circle, hit the Format Painter, going to transfer evaluation and measurement strategies, and voila. Next, I'm going to use a pattern to create the rest of the holes in this row. So with the circle open, I go to Nominal Definition Options, and I choose the Pattern command. You will see that there are 5 types of patterns available to us. Polar pattern offset for a bolt circle. 1D linear pattern, which we're going to use now for a straight line. A 2D linear pattern for a grid. A rotational pattern used for a scallop. This is when you have a hole that is incomplete and you need to have a strategy that skips a keyway or some other interrupting feature. And finally, pattern with position list. We have a bunch of holes that are the same size, but their locations are random on the part, and I can either load a text file or type in the XY locations of a bunch of holes. In this case, we're going to do a linear pattern, and I'll click OK. This opens up the 1D linear pattern definition template. Notice that it is currently relative to the base alignment. My offset is 0.55. That is the distance between the holes. There are 5 holes total. You'll notice that this does not seem to be going in the correct direction. That is because down here I currently have the Z space axis set. But when we're doing a pattern, most of the time the space axis of the pattern should match the space axis of the feature that we're actually using. So this feature uses an X space axis because that's the direction the feature is pointed. So here I change to an X space axis, and now we can see that our pattern goes in the proper direction. There is also a rotational angle here that can be used to rotate the pattern when necessary. For example, if I needed to put it at a 40-degree angle. Clicking OK and closing it.
What if they were in a... if they're... Oh, never mind.
Oh, as I said, one last thing is if I do have to skip a hole for some reason, there's an exclude index, and I can simply check any holes that I do not want included in the measurement, and I can simply add those back in. If you need to do a variety of things, you can select as many holes to skip as you wish. Click OK. And OK one more time. I'm sorry, excuse me. We do need to get the diameter. So there's diameter, and you'll notice that after I've gotten diameter, there is a position checkbox right here. I check this, and I'm going to go ahead and put in our tolerance, which is 14 thousandths. Now I'll click OK. I'm going to go ahead and go to our characteristics list. Here we can see diameter. Let me point a few things out. First, we see circle 5 now has a 5 in parenthesis after it, indicating it's a pattern with 5 holes in it. Also, the diameter here has a 151. It's going to measure the diameters from 1 to 5 in steps of 1. This is a typical loop designator. And then inside of our true position, we can see that our feature here, it says circle 5 and actually has a star after it. The star meaning this true position will apply to all 5 holes. If I open this up and look at it on the list, I see that I can still access any of the holes individually or the entire pattern as a group. I can apply tolerance in either fashion. I'm now going to set my datums. I can go ahead and click here where it says primary datum base alignment, and I'll select datum A. Next, I'll get datum B, and finally, datum C. We see here that all of the nominals have been properly plugged in, and we have our tolerance. Next, I'm going to set my maximum material condition. If I wanted to change the tolerance for the diameter, I could click this button, and now I'm inside of the circle characteristic where I can edit tolerance if necessary. Now I'm going to use F9 to test run my circles. You'll notice that this dialog comes up. This is in case I don't want to run all 5 circles in the pattern. I have the opportunity to run less than the entire pattern, and right here are examples and instructions on how to do that. In our case, we're going to run the entire pattern. And we're good. By the way, if we wanted to see our results, we simply have to open this up, close it, and then we can go View, Custom Printout. Notice it only prints the last one. We have to run the actual program to see everything. Now, on the true position, sometimes we want to output the X and Y value, or in this case, Y and Z values, more than just getting the true position. If we want to see the additional position information with the true position highlighted, we can go to Resources, Characteristic Settings Editor, and here you see the additional position result setting, which we can turn to on, and then click OK. And now, when we open and close our true position and look at our custom printout, we will see that there is additional information on the location of the hole itself. Next, we're going to do the overall thickness of the part using a point in Z. When we measure something that is a single point, we do not use the Define Points tool. Remember, that should be Define Probings. A single point is a space point. So I'll activate the space point tool. I'll come down here, and this is a point where on the real machine, I would normally go to CAD, CAD Model Control, and turn on Show Probe Object, so I can see my physical probe. I would then drive the probe underneath the part so that I can see where I'm about to program the point and make sure that I'm not hitting the support or clamp or anything else on the real part. Once I've tested that location, I can program my point. For this point, you'll see that it came in with a clearance plane of +Z, but I cannot go straight through the part to this point. So I have to adjust the clearance group to +X. One of the things to remember in Calypso is that when I'm using the negative x stylus, I should almost always use the positive x clearance plane. Paired opposites. Minus z stylus plus z clearance plane. Minus y stylus plus y clearance plane. And in this case, the minus x stylus, so we use the plus x clearance plane. I want to know the overall thickness, so I simply check the box. It is a single or simple characteristic. Next, we're going to check the profile of the plane on the back side of the part. Flip it around. Here we go. Extract features. Where's that new plane at? There we go. And open it up. Create a simple scan pattern. Oops. Looks like I already started making some points. I guess I'll continue with those points. You know what? On second thought, I think that all points is not going to be good enough for this measurement. So instead, I'm going to go ahead and highlight my single points, and I'm going to use this tool, which is the single points to auto path switch, which allows me to convert my single probings into a polyline. Now, this switch works both ways. I can always take my polyline and switch it back into single points if I decide that I do not want to scan this feature anymore. In this case, we are going to scan it because it's a profile. There's our polyline. And once again, up top, I'm going to use 480, double my maximum accuracy speed. And because I'm measuring a tight tolerance profile, I'm going to drop my step width down to the minimum step width without taking special precautions, which is 2/1000ths of an inch. I'm going to click OK. OK. When we scan, we filter, and when we filter, the default setting is always correct. Click OK. And finally, I'm going to come up here, Form and Location, Profile, open that profile up. Now I can select my feature from the list. Notice it only shows me those types of features that are appropriate choices for this profile callout. No circles or anything. In this case, plain. I'm also going to use the primary datum structure, oops, going slow here, sorry, B, and C. Finally, I need to set my tolerance zone. Currently it's set to bilateral 1 result. Most of the time when checking profile, we in fact want bilateral 2 results, so we get both the minimum and maximum values. Let me apply the true position, the profile tolerance, and our profile is now complete. And of course, I will test run that feature as well. And looks good. The final characteristic is in fact uses the first feature that we measured as part of this program, and that's the the flatness of the primary datum. You'll see under flatness that there are 2 types of flatness. Normal flatness is this first one. The second one is when you have flatness with a reference length, 1 thou per inch, for example. We'll choose regular flatness, open that up. Again, I'll switch to the Select Already Extracted Features and get the top datum plane. Now, I'm not sure if I programmed enough points in plane A, so I can click on this button, hit the Edit button, and now I'm editing the plane itself, and when I look, oh yeah, that's plenty of points for this measurement. Let's look at our strategy. Oh, you know what? I was taking points every 5/1000ths. I'm going to take points every 2/1000ths now that I have a 1/10 flatness I'm trying to evaluate. 6,475 points, still less than 10,000, so no substantial slowdown to the computer, and everything looks good. As I click OK to everything, we'll see that I'm now back in the flatness characteristic and can go ahead and put my tolerance in. I already have an actual result because we ran our plane A as part of our base alignment. Click OK and hit Save, and my program is now complete. I can now run the entire program. Plan, CNC Start. I've already done the manual alignment. All settings are the same. So now I can open this up, change it to the 3rd item on the list, which is always the name of my program and has this special icon next to it, and then I can click OK. And there are results. As I look at my results, I see that this is a large, clunky printout, and maybe I want a different printout. Resources, Define Printout, Custom Printout, and instead of the default, I'm going to use the default compressed tall icon. Okay, now I can go View, Custom Printout, and we see a little bit more succinct printout. And that's it.